In this video, we're going to be looking at a couple of formulas that are related to binomial distributions. One of them is for expected value. And remember that expected value basically means average, mean outcome. So we're going to be looking at the mean of a binomial distribution and then also the variance of a binomial distribution. Remember that variance is a measure of the spread. Mean is what's called a measure of central tendency. It talks about what's going on sort of in the middle. And then the variance and then the standard deviation also are measures of how spread out the data is. So a couple of formulas, and I'm going to offer these without proof because the proofs are fairly involved and really beyond this course. But they do expect you to be familiar with the formulas and be able to use the formulas. So it says, let's suppose that x is a binomial random variable with parameters n and p, so the normal n and p, where n stands for the number of trials and p stands for the probability of success. So we can say, therefore, that x follows a binomial distribution, again, with n trials and probability of success p. So the formulas we're going to be looking at, first of all, for the mean of x, and I just want to stress again that mean means expected value. Or expected value means mean, one or the other. And the formula for that is simply going to be n times p. So the number of trials times the probability of success. The variance is going to be n times p times 1 minus p. And I just want to point out, remember from before, that standard deviation is always the square root of variance. Standard deviation, not standard variance. Standard deviation is the square root of variance. And so that means that the standard deviation would be the square root of np times 1 minus p. So I just want to point that out from before. I don't think they even ask you to do that in any of the problems, but just wanted to mention it. Okay, so we're going to look at example 9, and that will include problems that will have both of those formulas. So it says a biased dice, I would say biased die, is thrown 50 times, and the number of sixes seen is 12. So when they say biased, it just means that it's weighted in some way. So we might have 6 sides to this die, but we don't have an even probability of getting each of the different numbers. And then it says, if the die is thrown a further 12 times, find, first of all, the probability that a 6 will occur exactly twice, the expected number of sixes, then it means the average number of sixes, and then the variance of the number of sixes. And I want to point out here, it wasn't clear to me when I first read this problem, when they ask for the expected number of sixes and the variance, they're only talking about this further 12 rolls. They're not talking about the initial rolls. So when we first look at this, all right, we might say, okay, this could follow a binomial distribution if we let x, if we're right here, we're counting the number of times the sixes occur. So let's let x equal the number of sixes. And I want to make this clear here in the 12 rolls. So that means that we have something that has 12 trials, a fixed number of trials, and the probability of success is going to be fixed, and we're going to find that probability by using this experimental data that's up here. So we can say that x follows a binomial distribution with 12 trials, right? And then as far as the probability of success, the probability of getting a 6, we're going to use this experimental data up here. So we're going to say the probability that x is equal to 6 is going to be the number of sixes that we got in this trial, 12 over 50. So that's going to be 0.24, okay, because that's the same as 24 over 100, right? So 0.24. So that's our probability of success, of getting a 6. So in other words, they didn't outright tell us what the probability is. They gave us data from an experiment so that we could figure it out for ourselves. Okay, so then in A, we want, and we might also mention this sample space. So x could be, the number of sixes, 0, 1, 2, 3, all the way up to 12, right, if we're rolling it 12 times. For the first one, it says, what's the probability that 6 will occur exactly twice? So that means that they're looking at this formula, the probability that x is equal to x. And remember that the general formula, I think this is on your formula sheet, is n choose x times p to the x times 1 minus p to the n minus x. So in our case, the general formula will be the probability that x is equal to x is 12 choose x times 0.24 to the x times 1 minus 0.24 to the 12 minus x. And this is just going to be 0.76. We'll fix that when we go to the next line. So if we want the probability that x is equal to 2, then that's going to be 12 choose 2 times 0.24 squared times 0.76 to the 12 minus 2, which is 10. And you can put that into your calculator and work that out, and that turns out to be 0.2444, keeps going, so that's approximately 0.2 44. Yes. Okay, then for B, sorry, I was checking my answer. All right, for B then, they want the expected number of sixes. So remember that the expected number of sixes, and you could write it as expected value of x, or you could write it as mu, is simply equal to n times p. So our n was 12, our p was 20.24, so that's going to be 12 times 0.24, and that one turns out to be 2.88 when you round that. And again, I'll let you check that with your calculator. For C, it says, what's the variance of the number of sixes? So the variance, remember, we can write variance of x, or we can write sigma squared, is equal to n times p times the quantity 1 minus p. So that's simply going to be 12 times 0.24 times 1 minus 0.24. We already have that number. We know that that's 0.76. So it's just 12 times 0.24 times 0.76. And that turns out to be 2.1888. So if we round that to 3 sig figs, this is going to be 2.19.